Hey guys, Pooch44, it's me here back at it again with another chem video starring me, myself, and my good friend Christina Dazos. Today's topic is kinetic molecular theory. Before we begin, let's discuss the particles in an ideal gas. These include they have no volume, they have elastic collisions, they are in constant, random, straight line motion, they do not attract or repel each other, and they have an average Ke directly related by Kelvin temperature. Gases can be diffused. Diffusion is just when a high concentration of gas particles move to a low concentration, or in other words, spread out. Diffusion is faster at higher temperatures because the gas molecules have greater kinetic energy. An example of this is if you place a tea bag in a hot cup of water, the stuff inside tends to spread out faster rather than if you place it in a cup of cool water. An example that doesn't pertain to heat includes when you spray a bottle of perfume, the scent tends to spread across the room due to diffusion. Gases exert pressure. This is done by the collision forces. The more particles that hit the walls, the higher the pressure. This was mentioned earlier in the particles of an ideal gas slide, which mentions that there are elastic collisions. Gases can be compressed. They have no volume, which means they have lots of empty space. The comparatively greater space available between gas molecules and atoms makes compression much simpler. Gases can be compressed much easier than a liquid or solid, since its atoms are spread out more, while a solid or liquid's molecules are packed close together or just very tightly. What is amount in terms of a gas and what variable is used? The amount in terms of a gas is moles, which is spelled MOL in shorter equations. The variable used is N, also used in equations. The mole is used for labeling the certain number, while the variable is used for writing out the equation itself. If this sounds confusing, compare to car gas. Moles to gas is the amount, just as gallons to car gas is also the amount. When you go to get gas, you ask how many gallons you have. So when you're speaking of regular gases, you ask how many moles they have. How is volume of a gas measured, in what units, and what variable is used? The variable used is a capital V, the units are liters, and it's measured in two different ways. One is by using a gas syringe, which withdraws a certain volume of gas from a closed system or chemical reaction. The other way is with Boyle's law. The volume is equally proportionate to pressure, with temperature being the constant. This relationship is inverse, meaning that less pressure is more room. A perfect example of this, also relatable, is when you go out to eat and you either wear jeans or sweatpants. When you wear jeans, there's more pressure, therefore there's less room for your stomach to expand, so to be comfortable you have to kind of go easy with whatever you're eating. However, if you wear sweatpants, it is less pressure, which means you have more room for your stomach to expand and enjoy all the food you want to eat. Okay, next slide is how is temperature always expressed, how do we convert to Kelvin, and what variable is used. The variable for temperature is a capital T, the units are Kelvin, which is shown as K, and the standard temperature and pressure is demonstrated as capital STP. The temperature of the STP is 0 degrees Celsius or 273 Kelvin. Temperature is the constant when volume and pressure are being changed, and it's Y is proportional, which is just the Boyle's law, as discussed before. The Charles law is when volume is directly proportional to temperature when pressure is the constant. And below that is just the equation used for this. There are other units of pressure, such as ATM, kPa, and mmHg. The standard pressure, which is STP, is a convenient reference point to compare gases to. Other standards include the ATM, which is just 1 atmosphere, 101.3 kPa, and 760 torr. Atmospheric pressure is the weight exerted by the overhead ATM on a unit area of surface, I'm so sorry for that typo. It could be measured with a mercury barometer, which is a long glass tube full of mercury inverted over a pool of mercury. A fun fact, the pressure exerted by the way the atmosphere at sea level, aka the atmospheric pressure, happens to be 101,325 pascals, which is roughly 14.69 pounds per square inch. Now that we've finished with the information, we're going to move on to some practice problems. First, we're going to start off with converting Celsius to Fahrenheit. To do this, you do 9 over 5 multiplied by the Celsius degree given plus 32. So here are a couple examples that you're going to convert to Fahrenheit, and the answers will appear shortly. So pause the video if needed. Okay, so the answer to number 1 is 50 degrees Fahrenheit. Number 2 is 86 degrees Fahrenheit. Number 3 is 104 degrees Fahrenheit. Number 4 is 98.6 degrees Fahrenheit. And number 5 is 32 degrees Fahrenheit. The next set of problems is going to be converting Fahrenheit to Celsius. So this time the equation is a little flipped around. This time it's Celsius equals 5 over 9 times Fahrenheit minus 32. So the answer to number 1 is 0 degrees Celsius. Number 2 is 7.2 degrees Celsius. Number 3 is 21.1 degrees Celsius. Number 4 is 26.6 degrees Celsius. And number 5 is 32.2 degrees Celsius. The third set of practice problems, Celsius to Kelvin, gets a little easier. Now you're just adding Celsius by 273.15 to get your Kelvin. Okay, the answer to number 1 is 273.15 degrees Fahrenheit. The answer to number 2 is 223.15 degrees Fahrenheit. The answer to number 3 is 363.15 degrees Fahrenheit. And the last answer is 253.15 degrees Fahrenheit. The final set of practice problems is Kelvin to Celsius. Again, this is a reverse version of the previous equation, being Celsius equals Kelvin minus 273.15. Okay, so now you can try these problems and the answers will appear shortly. Okay, so the answers. Number 1 is negative 173.15 degrees Fahrenheit. Number 2 is negative 73.15 degrees Fahrenheit. Number 3 is negative 0.15 degrees Fahrenheit. And last but not least, number 4 is 76.85 degrees Fahrenheit. Well, these problems conclude our video on kinetic molecular theory, so I hope you enjoyed and learned something.